Hi, today we want to test this little AC switch mode power supply. Mains in, DC 12 volts, 1.5 amps out. We're particularly interested in how much noise there is and how that noise is made up on the output. To do this test we're going to use a Kikusui PCR2000M AC source. That'll generate the mains to drive this. It's variable frequency, variable voltage. We're going to measure how much power this uses using this Kikusui digital power meter, KPM1000. That'll tell us precisely how much power is going in. This will tell us how much power is coming out. Kikusui PLZ Electronic Load. We can look at the waveforms and the noise on this RIGOL DS4054 4-channel digital scope. Let's get on with the tests.
Where do we probe? Now this method seems natural, but it can give misleading results. The long probe wire on the ground return and the long wires from the power supply itself can pick up noise from within the unit which aren't really in the output. A much better way is with a probe like this with a little spring to connect the ground. There are no long wires and the probe itself is almost screened. Now you should probe here on the output terminals if you want to measure the output noise on the power supply. Or, if you're interested in discovering the source of the noise, look back and probe within the circuit. We'll have a look at one of those signals later on. Now we'll be taking screenshots and putting them on a memory stick so that you can see the results more clearly. Like this trace, for example. On this scope it's simple. Pop a stick into the scope and press a button. Done. This is a 4 gigasample per second scope, and it may show things that are too fast to worry about, things that can easily be filtered out in the final product. So we use bandwidth limiting to reduce the high frequency response of the scope. In this example, the two traces show the effect of bandwidth limiting. We've limited it to 20 megs. This is a signal without bandwidth limitation, and this is with it. Quite a difference, I think you'll agree. It's set like this. The screen shows that it's set and a little light comes on near the input socket for that channel. On this scope you can set this on a per channel basis. It doesn't have to be the whole 4 channels. So here's a waveform showing a 100 Hz ripple with lots and lots of noise coming out of the power supply. Gradually increasing the time-based speed reveals the nature of this noise. To see this in more detail I've taken screenshots. Here is the waveform with 2 milliseconds per division. As you can see the repeating pattern every 10 milliseconds, this comes from full wave rectified 50 Hz mains. If we now select a small portion of this signal, shown on the top trace, we'll see that a window appears and a magnified version of what's in that window in the lower trace. This reveals a higher frequency component which has a period of roughly 14 microseconds. This works out to be about 70 kHz, and it's a fairly typical switching frequency of this type of unit. Speeding the time base up further shows the switching transients on the waveform. 1 microsecond per division, 100 nanoseconds per division, and finally 50 nanoseconds per division. Switching the probing point to the output leads, which we said wasn't really the best way, shows that in this case the results are pretty similar to the correct probing point. An interesting effect with this power supply was its behaviour under no load conditions. The output becomes unstable, but don't worry, that is fairly common with this type of unit. Probing further into the unit shows the charge-discharge cycle of the capacitor just after the Schottky rectifier diode on the output side. You can see the fierce charging pulse, then the gradual discharge. It's these sharp charging pulses that spell disaster for poorly designed output stages with high ESR capacitors. The capacitors eventually boil and their contents finish up all over the board. Just to satisfy ourselves that we are seeing a true picture of what is actually happening, we'll now probe directly on the output contacts with our short spring wire probe. Yep, the signals still look the same as they did before. It can be helpful to have a near field probe if you want to see more of what goes on inside a switch mode power supply, safely. Probing around you can observe several interesting signals, particularly around the ferrite transformer. And finally, we'll see how efficient our little switch mode power supply is. On the Kikusui power monitor, this is volts, frequency at mains, milliamps out, watts out, and on the Kikusui Electronic Load, these are the volts and the amps on the output side. We turn the output on and we see 10.7 volts, 1.5 amps. The input current is now 175 milliamps and the input power is 20 watts. So 20 watts in, 16 watts out roughly, gives an efficiency of about 80%, which is probably reasonable for a power supply like this. But that's not the whole story. We haven't taken power factor into account. That's the subject of another video. Thanks for watching. Hope you enjoyed it. Bye.